We now want to discuss the issue of diffraction, and the issue of diffraction arises specifically from a Huygens principle analysis of light. So recall that Huygens principle says that when you have a plane wave of light, each point along that plane wave can act as a potential point source of further waves. And so, when you have a plane wave hitting a barrier, for example, um, if these are ocean waves and these plane waves are coming in and they hit barriers, as long as the barriers have slits, some of the waves will make it through and they will create their own new spherical wave patterns on the other side of the slit. Now, we already saw this in double slit double slit interference, rather. But we're going to see how this principle applies to light and how it will affect things when you have either only one slit or multiple slits, right? And by multiple slits, when we look at the diffraction grating, you can have potentially thousands of them, for example. But what types of phenomenon do you observe? Well, when you have, for example, small objects that can be illuminated by coherent sources of light. Now, remember, coherent means that all of the waves coming out of your source are in phase with each other. When you have that situation, the coherent light hits your object, and that light will not just simply be blocked by the object and illuminate around it. The light will bend due to the way that the waves spread out. So when the plane waves hit an object, they will not just be blocked by it, but they will spread out. And depending on the situation, they can actually form so the waves will spread out spherically, and as a result, they will interfere with each other on the opposite side of your object, and that's exactly what you're seeing here. So you're seeing a central bright spot where this laser light has interfered with itself. All of the spherical waves that went around the ball bearing have interfered with themselves at that point, so you get a bright spot, but then you see the circular pattern radiating outward, and those are the areas of interference where the diffracted waves have interfered with each other once again. So, how do situations like this occur? So, the simplest analysis happens when we have a single slit. Okay, so we're going to say that our slit has a width A. And when you send plane waves at such an arrangement, assuming that the slit is not much bigger than the wavelength in question, such that they would just pass through. Assuming that's not the case, then you will see a pattern like that shown on the screen, where you have a very bright central spot, and then you'll get a pattern of dark and bright fringes that spread out on either side. Now, this is reminiscent of double slit interference, but the phenomenology is slightly different. Okay. And so, why do these patterns occur when you only have one light source? and only one slit. That's really more the variable here as opposed to the double slit experiment, is that you only have one slit. Why do you still see this type of pattern? Well, when you consider the plane waves coming through the slit, once again, each point along the slit can act as its own wavefront. And so when you consider the pieces of each wavefront that go straight through, or that they're pointed radially straight, they will just simply continue moving on. But for the pieces of each wavefront that get bent, okay, so remember, what's happening is this, right? And maybe let's choose red. What's happening is your wavefronts are plane waves until they hit the slit. Ugh. And then on the other side, each of these is its own spherical wavefront. And so each of these has a vector that's pointed this way. Oh my goodness. And each of these has a vector that's pointing this way out of the spheres. That drawing's getting busy already. But so out of a single sphere front, oh my goodness, I apologize. I might stop trying to draw because it's constantly trying to upload. But in any case, when you have a wavefront, you have waves coming out perpendicular to the wave, and when you have successive wavefronts, you'll have another one that's has individual waves pointing like this. So in each case, you'll have waves that are parallel with each other from different wavefronts. That's the bottom line. And I apologize for the drawing and for the haphazard nature of the PowerPoint here. But in any case, right, so each of these waves that you're seeing, these rays in this diagram, they can be from the same wavefront. Okay, so what I'm saying is this one and this one can be from the same wavefront, and this one can also be from that same wavefront. So, your wavefront has waves pointing in all directions. So each of these represent lines that are coming off of the same wavefront, okay? So when do you see these bright lines and dark lines, right? What produces the fringe pattern that you see? Well, remember, in double slit interference, this was the condition. If we replace the width of our slits A here with the distance between slits, in this formula, this gave the bright spots, but here we're claiming this is the dark spots. So what's happening? Well, when you consider when you have the path length between your nearest ray and your furthest ray, when that path length between those two is a multiple of the wavelength of light used, then what you have is halfway between them, you have a ray that is out of phase by half of a wavelength. And that middle ray is going to cancel with this ray, and the ray right next to it will cancel with the bottom ray. And so you'll have half rays that are canceling throughout the entire process under that condition. So when the sine of theta is equal to the wavelength divided by the distance. Now they're changing nomenclature here. They used A as the width of their slit here, and that's what they're using as D right here. But in any case, A sine theta times m lambda, and you can see the same thing happens when you go to a path length of twice the wavelength. So here m is equal to 1, here m is equal to 2, and so on. And so these are when the paths halfway between cancel out on either side, and you get that halfway cancellation throughout the entire situation, through the entire array, essentially. So every ray will have an exact half integer wavelength that it cancels with. But when the path length between the shortest ray and the longest ray is a multiple of half of a wavelength, then you don't get that. So what happens is the ray in the middle will constructively interfere with the ray at the very edge, because this ray in the middle is exactly one wavelength out of phase with, or I shouldn't say out of phase, it has a path difference of exactly one wavelength with the top ray, and as a result they will constructively interfere. And then a ray slightly below that, whose path length is different from the top ray by half of a wavelength, will constructively interfere with the 3/2 wavelength down here, and so here you get positive interference. And so for dark fringes, your formula will be A sine theta is equal to ml. For light fringes, your formula is approximately A sine theta is equal to m plus 1/2 theta, right? So now, one thing that needs to be noted here is what m runs through, right? So here m is equal to 1, right? So you don't have a bright fringe at m equals 1/2. You don't have a bright fringe at m equals 1/2. So your dark m will go from 0 to plus or minus 1. Oh my goodness. But for your bright, okay, so these are for your non-central maximum. So your central maximum, okay, is still going to be at a m equals 0. Okay, so you will get a bright intensity when m is equal to 0. So I guess we really should erase that part. So your central maximum is still going to be when m is equal to 0, and it will be, you'll use this with m equals 0 for the central bright fringe. Okay, but you'll use m is equal to 1 in both of these formulas thereafter. Okay, so just so you're aware. All right. And so because and by the way, this is approximate. Okay, the reason I wrote this as approximate is because this is exact for the dark fringes. Okay, this is exact for the dark fringes. You'll be able to calculate exactly where the dark fringes are from that, but the width of the bright fringes changes. Okay, the width of the bright fringes changes, and as a result, the bright fringe will effectively be halfway between each dark fringe, but because the width changes with the sine of the angle, you can't just use the m is equal to 1/2 to calculate it 100% precisely. But in most cases, it's a really, really good approximation. So that's why the approximation symbol is there. Okay. And so what you'll notice, right? What you'll notice is that in most cases, what you'll find is that your central maximum is extremely bright, and it will be the widest one. Okay, it will be the absolutely widest one. And it will have an intensity equal to the intensity of your source. Okay, you'll measure this to be at an intensity very close to the intensity of your source, and then your maxima on the either side will be much smaller in most cases. Okay, so you have a really wide central maximum, and then you have varying width maxima on either side, and as the widths get longer, the intensity gets both less, and the gaps between them increase. So the width of your dark spots kind of increases as well, and that's exactly what we're seeing here with this pattern. Now, you may be wondering, we talked about interference in the last chapter, and we're talking about diffraction in this chapter. Does diffraction occur in double slit interference? I mean, after all, it's light passing through a slit, and we're arguing right now that light passing through a slit should be diffracted. So does the double slit interference cause diffraction? And the answer is yes, it does. It's pretty much the main component that causes the light to actually interfere with itself. So when you apply Huygens' principle and the light point sources turn into their own wavefronts, it's those wavefronts that are interfering with each other. So basically, you have interference of diffraction. Okay, you have interference of two diffracted waves effectively. So what you have, if you had no diffraction, okay, in a double slit experiment, if you had no diffraction, you would get an intensity on a screen equal to the purple line here. Okay, you would have an intensity on the screen equal to the purple line. This line right here. Right? So you would not see a decrease in intensity on either side if you had pure interference without diffraction. The blue line right here, right? So the blue line is what you get with just diffraction. Okay, so that is your pure diffraction pattern. So when you superimpose the two, you actually get a very maximum central peak with near unity intensity, and then that dies off on either side such that the what would be the maximas on either side of the central maximum for interference get cut off by the envelope of the diffraction pattern. And so you get a pattern that is the result of both the interference phenomena and the diffraction phenomena. So this is why the double slit interference behaves the way it actually does. Now, double slit interference, what about diffraction gratings? What about when you have really, really, really thin diffraction gratings? What you actually see in this case is you still see a central maxima, but then you see really bright slits on either side with really dark gaps in between. And what's happening here is a complex interaction between the interference and diffraction effects that effectively basically cancel many of your secondary maxima out. And you only get these really prominent maxima at very specific points. So how can you calculate those? Well, when you have a diffraction grating, what we do is define this quantity D to be, give it just a second here. So we define the quantity D to be the number of slits per unit length. I'm sorry. We denote that to be the width of a slit. Okay. So D is the distance between slits, if you will. It is the slit width. Okay. So D is your width between your slits. And usually D is calculated by taking the total length let me call that L. Okay. So L is the length of your grating, and let's let there be n number of slits. And so in that case, D is going to be equal to N divided by L. Okay. And so, I'm sorry, it's going to be L divided by N. Okay. So you take your total length L divided by the total number of slits, and that gives you your slit width D. And under that condition, then just like with the double slit interference, the formula is pretty much the same. Once you have your distance between your slits, the formula works out to be exactly the same, where your maxima are going to be found by this particular formula. Now, there's really not a formula that we use for the minima, because the minima are so wide and the maxima are effectively lines, very thin lines. So what you can do, though, pardon me, if you're so inclined, would be to use this formula to calculate where the maximas are, and then just take the difference between those to calculate the width of your minima, right? That's usually how it's done. Now, this is for monochromatic light, but what happens if your light source is not monochromatic? What happens if you have a white light source? Well, when you shine white light through multiple small slits, what you get is, at the very center, all of the light has combined to keep the light white. But because the spreading out of the light is dependent on the wavelength, right? Because it's dependent on the wavelength, each wavelength is going to spread out slightly differently. So what happens is your reds are going to spread out further than your blues, and as a result you see a spectrum. And not only just one spectrum, but you see multiple spectra. So you will see two dominant spectra on either side of your central maximum, where your white light is, but then you'll also see a secondary spectrum beyond those, to the right or to the left, or up and down, depending on how your diffraction grating is oriented. And so the diffraction grating, when you have really, really tiny slits, is very good at creating these spectra, right? You can actually get individual spectra. And if you've taken high-level chemistry, or if you've studied any astronomy, you know that the spectrograph is one of the most important instruments for helping break light up into the components of an object, or an object's light that it emits, into its constituent components, and we can see what types of wavelengths from the spectra a certain type of object either emits or absorbs. Right? So diffraction gratings are incredibly important within scientific instrumentation. So in an example like this, if you have now this is from the textbook, right? And so it doesn't give the entire context of the textbook. But let me see if I can find it. So in this particular example, we've got 10,000 lines per centimeter. Okay. So for every centimeter of the diffraction grating, there's 10,000 lines. And so our D to calculate D in that case, okay, we would calculate D from there. And so from that, if you know the distance between your grating and your screen, you can use the trigonometry. You can calculate what the angle would be for each individual color if you know their wavelength. So, for example, if you use violet at a typical wavelength of about 380 nanometers, and you would use red at about 750 nanometers, then you can calculate what the width of this pattern would be on the screen, for example. Right? So, there you have it. I'm not going to work through that example right now, given how spotty my PowerPoint is being. But I will try to settle my PowerPoint down, and if I can, I will shoot another video here shortly, and we'll do a few examples that we didn't do here to help drive home these points. So stay tuned, and we will talk to you in the next lecture.